Hello friends, welcome to another lecture of vector calculus mathematical physics. Here the topic is vector integration. This video is especially for the BSc and MSc students, and this is lecture number 11. I will provide the previous lectures, link of the previous lectures in the description box. So before we start, please subscribe the channel if you are new to my channel, and share with your friends if you like my videos, and hit the thumbs up button. Also hit the bell icon so that you get notified when new video will be uploaded. Okay, so now let's start. So suppose here you see line integral. Let us discuss about line integral now. Suppose this is the coordinate system, and here is the origin O. Here we have a point on this curve. That point is P and the curve is AB, and here you see this is the function here F, and here is the tangent PT, right? So let us consider F of x, y and z be a vector function and curve AB. Line integral of this vector function is given by this vector along the curve AB is line integral of this function along the curve AB is defined as the integral of the component of f along the tangent PT to the curve AB. So component of f along that tangent PT will be given by at P will be given by dot product of this function and the unit vector along PT tangents. So f dot dr by ds is the unit vector along this. So where dr by ds is the unit vector along the PT, right? Where ds is a very small element of this curve, right? So that's what, and dr is the dr by ds is gives the variation of the or a change in or you can say displacement along this PT, right? Along this curve. This is very small element ds. It is a very small element of this curve, right? So hope you have understood this. So now line integral will be given by sum of f dot dr by ds from A to B along the curve, right? This line integral will be given by, so because here you see the component f along the tangent PT at point P. This is at point P, so we need to find the line integral so along the curve whole curve AB, right? So that's why we need to sum up, right? So sum up the component of f at each and every point on this curve, right? So then you will get the line integral. So now line integral, let me write it again. So here, so if you integrate to obtain the sum, if you integrate with respect ds, which gives the ds is the element of the curve, very small element of the curve. So here this c represents the integral along curve here. So then you will get this. So this is what you see. This is the line integral along the curve, right? AB. So now if this f represents the force, variable force acting on a particle along the curve AB, then the total work done will be given by this integral from A to B, integration of this, right? So, and if the total work done is 0, then work and energy is conserved. We can say work and energy is conserved. That's what we can say. Now to represent the integral along a closed curve, closed curve, here you see this is the integral symbol. We're going to use this to represent closed curve, right? So then this is a integral along a closed curve. This symbol is used. Now you see, let us take a question so that f, this function f, vector function f, is a conservative function force, and find the scalar potential of this function and find the work done moving an object from this point, from the point 1 comma minus 2 comma 1 to 3 comma 1 comma 4. The solution will be, so this is the given function. Let me write the given function here. So this is the given function. To show it is conservative, just you need to find a cross product of del n f. That means you need to find a curl. If the curl is 0, then it is conservative. So let me find using determinants. If you evaluate this, then what you will get. So I cap, that's going to be equal to derivative of this one with respect to y, right? And minus derivative of this x square with respect to z, both 0, right? And then minus j cap. So again, derivative of this trisect z square with respect to x minus derivative of this term with respect to z, right? And doing so we have got this. So similarly, plus k cap. So derivative of x square with respect to x, derivative of this with respect to y. If you do so, then what you will get? This result. So then you can see it's become 0. So f is conservative, right? So let me write the function again in order to find a scalar potential. So if phi is the scalar potential, then we can write that f dot dr must be equal to, so if phi is the scalar potential, then f dot dr vector should be del phi dot dr. Okay, so now let me continue here. Dr is nothing but dx I cap, dy j cap, dz k cap, right? So this is the dr vector, right? So here you see, okay, if you find a dot products, we're gonna get this result, right? So now this is the total derivative of phi scalar potential, and on the right hand side, if you rearrange it, then you will get this expression, right? So now you see, this part you can express as a derivative of product of x square and y, and the next part here you see, this part can be expressed as derivative of product of x and z cube, right? That is del phi d phi. If you integrate both sides, then you're gonna get phi is equal to this plus constant, right? Integrating constants. So our scalar potential will be only phi will be equal to x square plus x square y plus x z cube. This will be the required scalar potential. So now you see, we need to find the work done in moving an object from this point, from this point 1 comma minus 2 comma 1 to this point 3 comma 1 comma 2, 3 comma 1 comma 4. That work done will be given by the integral from this point, initial point, to the final point, vector f dot dr vector. So, and f dot dr is nothing but you can write del phi, right? If you integrate del phi, that's you're gonna get phi, and we need to put the upper and lower limits, right? So del phi is equal to this. So this is the scalar potential. So these are the points upper and lower limits, and required scalar potential is this. Let me write here. So now let me write the value of w expression on the other side, and putting the upper limit and lower limit, putting this upper and lower limits, we will get the value of w. That means we're gonna get the work done. So let me go to another slide. So w is equal to, we have got this, right? Now let's put the upper and lower limits. So we got these values. So just putting the upper limit, we have got this, and putting the lower limit, we have got this. And now if you subtract, evaluate and subtract, then you're gonna get this value. So this is the work done. That's how we can solve. So hope you have understood this. So thank you for watching. See you in the next video. Take care.